All right, today we're going to talk about a Nobel Prize-winning discovery that is so cool, so profound, it might actually give us the tools we need to build a better, cleaner world. So let's just dive right in.
It's this huge question, right? It sounds almost like science fiction, but what if the answer to our biggest, most overwhelming challenges, I'm talking climate change, clean water, what if the answer isn't some giant machine, but something so incredibly small you can't even see it? Well, that's exactly what this prize is all about.
So how in the world do you tackle a problem the size of a planet? Well, it turns out you start at the molecular level. This Nobel Prize isn't just celebrating some abstract scientific curiosity. It's recognizing the invention of a whole new class of materials that have almost unbelievable potential.
Yeah, the folks at the Royal Swedish Academy of Sciences honored 3 pioneers for creating what are essentially programmable materials. I want you to think of them like custom-built tools, designed literally atom by atom to solve one specific problem, whether that's capturing carbon or filtering out pollution.
So what are these miracle materials really? Well, they're called metal organic frameworks, or MOFs for short. I know, the name is a total mouthful, but the concept behind them is actually shockingly simple. Let's get into it using an analogy that I promise you will not forget.
Okay, so here's the official textbook definition. You got metal ions, which act like the corners or joints, and they're connected by these carbon-based organic molecules that act as the linkers. You put them together and they self-assemble into these perfect, repeating, three-dimensional crystals. But what does that actually mean?
It means you get a structure that is filled with trillions and trillions of tiny, identical rooms. And get this, gas molecules like carbon dioxide or even water vapor can check in, stay for a bit, and then check out. It's basically a super high-tech sponge, but with pores that are precise, right down to the atom. And by just changing the building blocks, you can change the size and the shape of those rooms, making them the perfect 5-star hotel for whatever molecule you want to catch.
And the process itself is just wild. It's almost like playing with molecular Lego. You choose your corners, those are the metal ions. And you choose your struts, the organic linkers, and you just mix them together in a solution. And incredibly, they know exactly what to do. They build themselves into this perfect crystalline cage that is absolutely packed with empty space.
Now, a revolutionary idea like this wasn't the work of just one person. It was really 3 key visionaries who, over about a decade, turned this chemical curiosity into a technology that could literally change the world. So, let's meet the architects behind this programmable matter.
And look at this timeline. The progression was just astonishingly fast. In only 10 years, the entire field went from a fragile, purely conceptual model to robust, dynamic materials that were ready for real-world use. Each step was a massive breakthrough that just built on the last. It all started back in 1989 with Richard Robson. He was the conceptual architect. He was the first person to realize you could use the natural geometry of atoms to build an orderly, 3D crystal that was just full of holes. Now, his first MOF was pretty unstable, but it didn't matter. He had created the blueprint. He gave chemistry its first ever molecular floor plan.
Okay, next up is Susumu Kitagawa in Japan. In 1997, he created MOFs that were flexible. I mean, they could actually breathe. They would expand to absorb gases and then contract to release them, all without falling apart. He took a rigid solid and turned it into something dynamic, a material that could literally inhale and exhale chemicals. It's amazing.
And that brings us to Omar Yaghi, the master builder. In 1999, he created the masterpiece MOF 5. This was the game changer. It was incredibly stable, it could handle high temperatures, and it was just astonishingly porous. He had built the molecular Airbnb that was finally open for business.
And when I say astonishingly porous, I mean the scale is almost impossible to wrap your head around. The internal surface area that's packed inside these microscopic crystals is just truly mind-blowing. To give you an idea,
I want you to just think about the entire surface of a football field. Every blade of grass, every painted line from end zone to end zone. The whole thing. Now imagine taking all of that area
and cramming all of it into a single spoonful of Yaghi's MOF5 powder. That's the power of this technology. An absolutely incredible amount of active surface area for molecules to check into, all packed into a tiny, lightweight material. It's just nuts.
So, okay, we've built these incredible molecular structures. We get it, the science is cool, but what can we actually do with them? Let's check into the real-world solutions that these materials are making possible right now.
The key here, the magic word, is specificity. There are tens of thousands of different MOFs, and each one is a custom-built tool for a very particular job. Take Calf 20, for example. Its pores are the perfect size and shape to act like a CO2 magnet, snatching it right out of industrial smokestacks, while other gases just pass right by. Or Moth 303, which is so good at attracting water, it can literally pull a liter of pure drinkable water out of thin desert air. Others are designed to trap toxic forever chemicals or to safely store the clean fuels of the future, like hydrogen.
So, here's the crucial point. This isn't just about one new material. It's an entirely new way of thinking about what materials can even be. We've moved from just discovering materials out in nature to actually designing them, atom by atom, for our exact needs.
I absolutely love this quote because it just perfectly captures the spirit of this prize. This is not chemistry for destruction. It's chemistry for construction. It's for healing the planet. Robson, Kitagawa, and Yaghi didn't just mix chemicals, they redesigned space itself. And to really understand the potential impact here, think about it like this. If plastic was the defining, world-shaping material of the 20th century with all its good and all its bad, well, MOFs could very well be the defining material of the 21st. Only this time, they're designed to clean up our messes, not make new ones. And this is really the ultimate takeaway. We can now design the empty space inside a material to perfectly fit a specific molecule we want to capture, or store, or even change. We are learning to program matter itself. So the Nobel Prize is for the incredible work that's already been done. But the real excitement, the real story, is about what comes next. Now that we have this unbelievable toolkit, the question is no longer can we solve these problems, but which ones do we choose to solve first? The future is wide open.